Okay. Let's see. Hello, Joan. Hello, Jack. My God, Jack, what are you doing up? Uh, wow, that's a great picture. Uh, what are you doing up? Um, and welcome, Joan. Uh, and welcome, Sabine. Uh, and so, so Jack, did you set an alarm to wake up at this time?
No, I actually haven't been asleep yet.
What?
Yeah, I haven't been able to fall asleep yet.
It's 4 o'clock in the morning there.
Very good, Dr. Laird.
God, I'm really good with that sort of thing. 5 hours I can add, and then I have to carry after the 12 and subtract. So yeah, welcome, Jack. That picture, for those of you who are looking, that's my grandson, and he is putting on his skis for the very first time. He's not yet 5, and that's my daughter, helping him with his skis for the first time. Wow, that's amazing. That's just amazing. Uh, but that's not why you're here, boys and girls. You're here to talk about astronomy, and and Jack, of course, if you have something to say about astronomy, please. Uh, you realize I'm going to do it now. Okay, Jack, I'm going to do what you said. Okay, this is Jack's idea. Jack's idea is that I should tell you something before we begin, and before I invite you all to ask questions. I should deliver some sort of factoid or even lecture. But I'm going to so I'm going to tell you some things or something to start the evening off, and maybe that'll inspire you to ask questions. So there's something very exciting, I think, that happened in the last week or so, at least to my knowledge, to the knowledge of the people working on it. Probably they've been known about it for a year, but it seems as if we have a new kind of astronomical body in the universe, something we didn't know about before. And it's really interesting. So what we know we have is there are things called planets and moons and stars and solar systems, and then after that, pretty much uh, molecular clouds, and then after that, pretty much galaxies. So that's what we know is out there in the universe. But there's something new out there, and that is in the Orion Nebula. And Jack, pay attention here because Orion is my grandson's name, named after the Orion, well, constellation. Uh, uh, in the Orion Nebula, the James Webb Telescope has discovered what is now been confirmed to be 40 objects, which are now given the name of jumbos. Jumbos, and they stand for Jupiter something something massive binary objects. Uh, and and what they found is there are two bodies, planet-sized bodies of the size of Jupiter and Saturn, orbiting one another in the Orion Nebula. And the thing about that makes it interesting is that according to everything we know about planetary formation, that doesn't make sense. So there are two possibilities of how that makes sense, because it's not like it doesn't make sense. It's like oh, we didn't think of that before. So now that we have evidence that something that we didn't know about exists, we immediately jump to ideas of how it could be. And there are two theories that I've read about at this point. Theory number one. See, the problem with making a planet is you can make a planet because it sweeps up debris in the interplanetary medium, and sweeps up debris, and you get yourself a Jupiter, you get yourself a Saturn. But you don't get yourself a Saturn orbiting a Jupiter. They never see that. And not only do they not see a Jupiter orbiting a Saturn, they've never seen that, but these Jupiter Saturn binary objects are not near any star. They're free floating. They are out there in the away from any star that they might have been born next to. Free floating binary objects like the size of Jupiter and Saturn. How could that be? So one possibility is that we know that solar systems throw planets out. We know that Jupiter and Saturn have been busy throwing out objects from our own solar system. Those things are called monarchs, and they're thought to be in the neighborhood of a tenth of the size of a normal planet, and or even bigger, and that the solar system has thrown out many of those in the course of its 4.5 billion year history, mostly in the beginning. But those things would have been solitary objects, not binary objects. We've never seen a solar system form a binary planet before. And these would be binary planets that get thrown out of solar systems. So that has to be the answer. Binary planets thrown out of solar systems. That's new. And the other possibility is that in the Orion Nebula, which is a star-forming region with thousands of stars being formed in a very small region of the nebula, that these binary planets could have been formed independently of a star. They could have formed just out of the gas themselves, which again would be impossible in terms of previous thought. So it's either one of those two things, and we don't know which one it is. So it's pretty new stuff. And furthermore, knowing that, we can also suppose that these objects are the rule rather than the exception, and that interstellar space may be filled with these things, and we just don't know. So it's like the universe, the most prevalent thing in the universe, which we used to think was small stars, could in fact be small planets. Small stars are the main kind of stars that are formed in star forming regions. But this is even smaller. So it would be the tail end of the small stars, and it would be the most numerous of them all. So that literally our space is filled with these rogue, gigantic, jumbo planets. So that's the news of the week in review, at least the one that fascinates me. Okay, so, and I lost the person who's on the stage. So, Jack, that was supposed to attract people. Raise your hands, and I'll invite you to the stage. That was like a come on. That was, if you come, I will answer your questions. But okay.
Does
So
this
in the meantime,
does this discovery possibly change the way we define what
do we what?
does this discovery possibly redefine, or could it redefine what a planet is, or how we define what the planets
It's not redefining anything. But Jack, your Wi-Fi in your apartment is increasingly, iffy. Because I only picked up some of what you just said. But so I only heard redefine. But I don't think it redefines anything. It just presents just a new and magical thing that we didn't know before that is going to be quickly explained because it's not like we don't know the conditions. The conditions that form stars and planets are very well known to us. So it's just a question of what sort of stuff you throw into a model in order to get out planets. And, and one of the things that's hard to throw into a model is turbulence and chaos. So it looks like they'll have to throw a lot more chaos into their models in order to get these planets out. So I don't think it's going to change anything very much, but it's going to be exciting because it gives us a whole new place to land instead of going from star to star, okay, uh, we instead of thinking that the nearest thing close to us is Alpha Centauri, it may give us the possibility that the nearest thing to us isn't Alpha Centauri, a star with planet, but maybe just a planet without a star. So that could be, and that means we'll start looking nearby to see if we can find anything nearby and close. And it's not as if we haven't been looking, but maybe they'll look better and harder. So we'll see how that you know turns out, and see how big. We'll see how big news that is. I like the word that they concocted for it, jumbos, and that's an acronym that's going to stick. So we'll see how that works out. Okay, so if you don't mind, Jack, I would thank you. Those stars, action, welcome. Thank you for coming.
Good evening, Dr. Laird. How you been?
Good, very good.
Great. I thought of coming to your room because I was having just some confusion between something kind of basic for you, I'm sure. I want to talk about light.
Mhm.
Um, so, uh, light photons are massless. Is that correct?
Yes, but that doesn't mean they don't have gravity.
Right, right. That's okay. But they're
Okay,
massless.
right.
So, and they're massless because they're going at speed of light, right?
Well, I don't know if I would add a because there. In other words,
I mean, if they had mass, they wouldn't be able to go to speed of light.
that's right. That's right. I would go
Right.
there. That's
So,
where
so,
I
we,
would go.
so now is that also correct that when a photon is not going at speed of light,
Well,
that would give it some,
it can't do that. It has to. It doesn't have a choice.
but photons can be slowed down, right?
Well, you mean in a medium,
Yes.
like like glass.
Yeah, or water or something.
Right, but I don't really think that it's slowed down. This is an area where I'm really unclear. So I've asked this question before, of myself. So in glass, photons are slowed down. But are you
Mhm.
saying that the speed of light in glass is slower? And I,
That's one thing that's confusing me
Right. Now,
because
so I've asked that question, and I've asked it of people who know better than me, and I forget the answer. Okay. Uh, so this is my answer, given my knowledge, but I could be wrong. I think that the speed of light in a medium like that is in fact not slowed down at all, but because of such a phenomenon as the re-emission of absorbed light, that the process of absorbing and re-emitting is the slowing down process. I think that's right.
okay,
There's a thing called Cherenkov radiation. Have you ever heard of that?
no.
Okay, so uh, if you send an electron through, say, a medium like, let's say, glass, okay,
Hmm.
and that electron moves so quickly that it moves faster than the speed of light in that medium, that electron will emit a certain kind of radiation called Cherenkov radiation, which again doesn't really answer your question. Uh, so your question is light slowed down inside of a medium, or is it just something other? And I'm
Well,
going with
actually,
other.
the question actually is that if light slows down and in a certain medium or something, um, and it's going slightly, let's say, even the minute percentage slower than the speed of light,
Yeah.
then it could have mass, right? Then it could have rest mass.
No, no, no. See, that's, I would conclude that based upon the logical points you've raised. I agree. Uh, but no. I mean, nobody has ever said that. So, okay. So
Okay.
on the basis of nobody's ever said that, I say no. But now I'm called upon to explain it to you, and I can't. In truth, I if we had a if we had a real physicist in this room, rather than somebody who studied physics in college, which is a big difference, I would. So, for example, the speed of light. Okay,
So
uh,
are you saying like the photons never are in
wait.
anything but 10 in speed of light speed?
Oh, no, yeah, I am. But here's the thing. There's a thing called Maxwell's equations. Have you ever heard of
Right.
that? You have,
Yes.
right? Okay.
Yes.
Now, in Maxwell's equations, there's two parameters. Okay, and those two
Right.
parameters are epsilon sub zero and mu
Right.
sub zero. And
Right.
epsilon sub zero is the permittivity of vacuum space, and and mu zero is the I'm not sure, magnetic something of vacuum space. So
Gauss law of magnetism? No.
no, it's not. It's not Gauss's law or anything. It's some other property of empty space. Mu
Okay.
zero. Anyway, so if you insert in Maxwell's equations those two constants, but they're no longer uh, um, for empty space, but for glass, and they are under the square root of, so it's 1 over the square root of those two numbers. So if those two numbers are bigger, then the velocity of light would be smaller, and that would be the the velocity according to uh, the Maxwell's equations. It's still not answering your question, but I'm positive that it doesn't gain mass because it slows down. That much I know. You
So
know.
no, I mean it doesn't slow down. What you're saying is it doesn't slow down, hence it doesn't have mass.
Well, I'm not saying it doesn't slow down because according to everything we know, gas light goes slower in glass, right? So I'm saying is
Mhm.
that doesn't mean that it's slowing down in the sense of that it's not moving at the speed of light. It's moving at the speed of light in that medium. You know what I mean?
Right. Okay.
You
It's
know what I
moving in
mean?
the speed of light in that medium.
In that medium, right? And nothing can go as fast as it in that medium. All the stories you tell about light would be true about it in that medium. You know,
So
I,
in EMC, in Einstein's equation, where c is usually taken as the speed of light, but
yes,
that c is actually causality, right? Like the speed of causality
yeah,
itself,
sure. Well, causality comes into it. Yeah, right. But, I
which is
mean, but
propagated through electromagnetic waves. So
right.
hence we kind of almost right. So so then what is this rest mass thing happening with photons? Like why is any kind of mass attached to it, and especially when we say energy equals to mass and mass equals to energy, right? So
Mhm.
then how are photons still massless?
These are good conversational questions that we really both need to ask of somebody who's uh, who's good. But nevertheless, I think, I mean, the stories that I've been told are if you, and you've been told this as well, so this isn't going to help any, but nothing can travel at the speed of light except something that doesn't have any mass. And there are a couple of those things. It's not just, by the way, electromagnetic waves. It's gravitational waves, apparently. It's also gluons, which are massless particles inside the atom, which are transfers of the strong force. I always find this crazy, okay, and crazy in the sense of that my classical brain can't imagine it, but the idea is the way that electromagnetism works is photons are exchanged between, the plus and the minus thing, and that those the photons are exchanged, and the way that they exert a force between the plus and the minus is through the electromagnetic waves that are being transmitted between the two. And and I go, oh, really? How do they know where the plus and minus is? But nevertheless, I that's the story that I know, and I also know that inside the nucleus, the strong force is mediated by the gluons which
Hmm.
is a form of energy, not mass, that is transferred between the quarks. And I think recently I read, which I find even more fascinating, is that most of the mass of the atom is not the quarks, which make up one third and two thirds kind of thing, but the gluons that are making up most of the mass, even though they're massless, because, as I've said, it's not like energy doesn't have gravity kind of thing. It still has the ability to pull and to be mass. So those gluons, which are making up the mass of our atoms, are contributing to the gravity that atoms produce. So massless particles are producing the gravity that we all enjoy.
That's just crazy. That's just crazy.
Right. Yeah, I know. I know. I know.
Right. I mean, I still don't understand the idea of light. I mean, what you're saying, like when I say it's crazy, I mean, just like you, I fail to sort of understand how, that would be possible.
Well,
Uh,
the reason that you and I don't understand it is because neither of us have looked at the math. And
or yeah,
we always say that physics is always in the math, right? We always say that,
right.
right? And then we go ahead and start talking about it as if we understood the math, where in fact we don't. So if we were really good physicists, you know, we would look at the math and go, aha, of course. And now we are challenged with explaining it to the layman. So we make up these stories, okay, which don't make classical sense, but we try to foist it off on the general public. But the physicists are happy because it works out. It's just that we're not happy because we don't understand it.
Well,
Especially,
I think I don't think like if you ask them that why is it doing this, they'll be able to answer you that. They'll just tell you how it's doing it, or like the math just says how is that possible, but
right.
not really whys.
Yeah, describe it. You can describe it, you can use it to predict. So you have a set of equations which then describe the phenomenon, and you can use that set of equations to predict other phenomena, which turns out to be true. So you say, the phenomenon is contained within the equations. Nobody ever explains the equations. You know what I mean? I mean, how did when God was busy inventing the universe, do you think he made choices? He said no. He said I'd like it this way, and not that way, and that's the way it is. I don't think in the end we understand anything about why ever.
So
You know,
if gluons were to travel, um, would they travel in the speed of light
yes, that's what's been said that gluons travel at the speed of light within the nucleus,
within the nucleus?
within the
If
nucleus.
can gluons exist independently if they are scattered or broken or something?
Well, that's a question for a particle physicist, and I know that they haven't been able to. I don't think they've been able to isolate quarks from the nucleus, but they
Uh-huh.
can still determine they're there. And I don't know how they determine all these properties of the nucleus because that's really the realm of particle physicists. And I gave up a long time ago trying to memorize the standard model.
Uh,
Yes.
and in terms of for speed of light, if I want to ask the question like, do you think, and this could be a stupid question, so do you think the speed of like a photon goes at the speed of light because it's massless, or do you think because it is traveling at that speed is why it has to be massless?
Let me see. Uh, I think both. I mean, the thing about hold, the thing about Einstein's theory of general relativity and special relativity is that you it shows that you can't have something with mass traveling at the speed of light.
Mhm.
It's just not there. It, only the energy part can travel at the speed of light.
But does that apply to everything? Like in the sense that if there's any particle that we know of or we find eventually that, let's say, gluons, for example, or it could be something else that don't have any mass, would they all also go at the speed of light? Like,
Yes.
do we
So
know
the
anything?
so I know that answer is yes.
Okay.
Okay. I just can't explain why.
No, that's
But
okay. Okay. As long. Okay. So there's consistency.
it's a definite yes.
Okay.
Yeah. If it's going at the speed of light, it's massless. If it's not going at the speed of light, it's it has mass. And those two things are true. Uh, and and the interesting thing though is the speed of gravity is has been measured to a certain percentage, like 99.99 something percent of the speed of light, plus or minus, and the speed of light falls within the error bar. You know what I mean? But they haven't
Right.
measured the speed of gravity anywhere near as well as the speed of light. And the reason for that is that they got lucky once, and they found the kilonova, two merging neutron stars
Right.
that were producing the gravitational wave, and they also able to identify it optically within, like, say, a day.
Mm-hmm.
And so that means 1 day out of 10 billion years. So that's the error bar.
Oh,
You know what I mean?
right.
They couldn't pin it down better than that. And the reason they couldn't is because when you get these gravitational waves, the gravitational wave detectors have very poor angular momentum, angular resolution. This kind of like this. Oh, the gravitational wave is coming from somewhere in the northern hemisphere.
Right.
Off towards Asia. You know, that's the kind of resolution they have. And
Right. I mean,
and
they are so big, so I guess, yeah.
Yeah, and if you look up in the sky with big telescopes, they don't work. So you have to look up in the sky with small telescopes with large field of view to find the thing. And it still takes a while to scour the whole sky. It takes like a day, I think, to scour the whole sky over China to see, what's cooking. They are
Right.
producing new telescopes, whose job it will be to see the whole sky every few nights, to see these things. You know, so we'll get a better handle on, the next gravitational wave that we perceive. But
Right. Right. Right.
speed of light is same as the speed of gravity to what we
Okay.
know.
Okay, that's pretty cool. So, I mean, for the flight conversation, I think that's good for me to kind of do more thinking and now ask better questions. I have something another question to do with time, but I can come back to that
No,
if you
actually,
want.
actually do it because there's two other people on stage. There's a lot of people in the audience, so let's entertain them. And
Yeah, yeah. Okay,
yes,
okay. So for time, I had a thought. Let's say at the Big Bang, when everything is expanding, let's have imaginary clocks because that's when time began.
okay.
And say billions and trillions of imaginary tiny clocks were also expanding along with the space and time.
Hmm.
Um, Now, if say I paused the time right now in this second, I pause it all around the universe, everywhere.
How do you do that? Just let me ask you, how do you do that?
I don't I don't know how to do that, but let's say I
No, no,
don't pause it.
it's
Let's say
hard.
I take a snapshot. Let's
You
say
could see, the thing is, you got to get everybody to agree
okay,
on
okay. So say
simultaneity.
somehow
The first thing that Einstein said is simultaneity is out the window.
okay. Um, so say let's say I have a device with those imaginary clocks. I also have a device that could report back to me the time of that clock to that one device,
Right. You
wherever
could,
it is.
so you can gather data from each of those clocks
Correct.
and compile it at home at your leisure. Yes, that's true.
Someplace, yes, at any given point in time.
Right.
So I was wondering if no matter what time I choose, especially now, if I choose to stop it now, and if I take a tally of all the clocks, they're not going to be at the same time,
Right.
right?
Of course not. Right.
Some would have gone closer to black holes and time dilation, some would have been somewhere else, etc.,
Right.
etc.
Oh, right.
So now we have different timelines across the universe in a
Congr-
way,
congratulations. You and Einstein have
right?
reached the same conclusion.
So now what I'm wondering is there, like, do they all meet somewhere, or do they just keep going on in their own timelines, or do they somewhere converge and then, like, kind of quantify everything? Does
No,
the when the black hole evaporates, does somehow that time that was dilated around it somehow catch up, or is it now just always going to be slowed down
it's
as we go?
so you imagine in your imaginary thing that the clocks were synchronized at the instant of the Big Bang. Okay.
Correct.
Okay. And now, 13.8 billion years later, the clocks have now sent you a signal telling you what time they are. Okay. Now,
Right, and they are not, for just this example, they're not traveling at the speed of light. So I mean,
none
there's
of them
no,
can.
yeah,
There's no problem there. No problem there,
yeah,
because
okay,
they're not. They're clocks. They're not massless.
right,
Okay. So they report to you. Now, the report is coming to you through space, which is expanding. All right. And so, at the very least, the report that you get is missing some information, which is what did the intervening space do? But I guess you could say, aha, I know how far away the object is and was at the
hmm,
time that it was emitted, so I can figure out
the delay,
what the delay was. So now I can
right.
check the clocks. Okay.
Right. Actually I was like, yeah, that is one way, but I was just assuming again for just the thought that they're, like, based on this way, for example, or some other math, that I could do that math, and that's not my problem. I
Okay.
will have the accurate time
Okay.
as it was synced earlier.
Okay.
Yeah.
But what are you saying
I'm
or asking?
wondering, yeah, so that's what I'm saying. I'm wondering that if those clocks ever come back to a same time, ever.
Oh, no, 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 no. If the universe went somehow contracted and got sucked back into the black hole that it came out of or something like that, no, no. Those clocks are forever. They've all had a look. The twins, you know the twin paradox.
Remind me again.
Well, you have two twins. One leaves on a spaceship, goes to
Oh,
Alpha
right, right.
Centauri, and comes
Yes,
back.
yes.
Okay, and
Right,
the one that goes and comes back is much younger. Okay,
right,
that twin is never going to get back. The older one is never going to get back his youth, and the younger one is going to be aging. Is always going to be younger than the older one. That's it. You
right.
can't fix it.
So there's no convergence.
Right. You can't fix it.
Right.
But what I think is most interesting, and this is what Einstein said, and this is a good thing to wrap your head around, which is that everybody in the universe has a watch. I like watches rather than clocks
Uh-huh.
because it's personal. And the fact is that you and I have watches, and we are, on the same planet, within certain miles of each other, and so you and I should be able to synchronize our clocks, our watches. The thing is, we can't. There's
Right, we
no,
can't.
we cannot.
Right.
We cannot do it. It's not possible. Okay, we
Yeah.
can
And that's, I think,
mathematic.
why also, so,
We can.
sorry, that's, I think, why we cannot measure the speed of light one way, right?
It's not that we can't. It's just that if you and I are standing apart, 1 foot apart, okay, and we say synchronize your watches, okay, that way, you know,
Uh-huh.
if we do it, one of us is going to is going to have a different time than the other, e- in two ways, simultaneity wise. First of all, we won't be synchronized in the first place, and we won't be synchronized thereafter as well. In other words, everybody in the universe has a clock that is unique to them, and nobody else has a clock anything like it. So
But
everybody's time is different. in the universe. That's the takeaway. That's the cool thing.
But say you and I are standing a feet apart, and
Okay.
we have our watches, which are say digital watches,
Yeah.
and they're
But
both
there's a
connected,
distance between us.
right? But they're both connected, say, to another device which is in the middle
No,
of
but
you and I.
that's still a half a foot between us.
No, so wait. So what I'm saying is, so there's a device in the middle of you and I, and that sends a pulse.
Haven't you ever seen the experiment in which it's a train, okay? This is the classical story of simultaneity, okay? There's a
Right.
train, okay? And the guy in the train sends a signal from the middle of the train car to the front and the back of the car, okay? Trying to synchronize the clocks forward and back, okay?
Right.
And that's what he's trying to do, okay? But the people on the ground watching the train go by see that one of the clocks is leading the other one because and how do you know that? Because when each clock receives a signal from the guy in the center, they send a lightning bolt down to the ground, okay?
Mm-hmm.
And the lightning bolt down to the ground should be equal to the length of the train, right?
Okay.
But it's not, it's shorter. And that's called
Okay.
the Lorentz contraction, which you can either interpret as in simultaneity or shrinking of spacetime. It's all
So
crazy.
simultaneity doesn't exist, right?
Yeah, simultaneity is something you can't achieve in moving objects. Uh, and remember, you have the gravitational field involved, okay? And remember, you have a difference in latitude between the two guys. So if you and I are standing at the same latitude, so we're traveling around the Earth at the same speed, uh, and we're at the same height, I mean, maybe we could achieve some sort of simultaneity, but to somebody else who's not standing at the same latitude, they would not
Hmm.
agree.
What about
So
entangled particles?
I don't know. I don't know about that.
Like do they like so like if you measure one, then the other one is the other
Yeah,
spin,
I guess what they say is simultaneously,
right?
but but I don't know whether they're taking into account what I've just said.
Because it doesn't go as speed of light, right? It's not something that's traveling as a signal.
No, it's
So it's
instantaneous. It's
correct.
instantaneous.
So wouldn't that be considered under something which is happening simultaneously?
I would offer that that's a good argument. Why don't you check with somebody who knows? Because this is good. I like it because I've always said simultaneously, without for a second questioning the question of simultaneity as being achievable. So I don't know what that means in the sense of uh, I guess it has to take into account the simultaneity of I don't know. You stump me.
But I like having these conversations because then I know what to search for. I know what to look into. I know where to go because then I can get the basic stuff out of the way,
Yeah,
which you tell me, and then I'm like, okay, so this is what I'm searching, or this is what I'm looking up at. This is
right.
good.
So
I like it.
you want to ask the question. I would Google, is simultaneity possible, or is it possible to synchronize watches at all?
Well, perhaps not, but yeah, perhaps not watches because maybe it's something that is following this I don't know speed of light because it has a mass, it has a thing, but
Yeah,
then something like uh, simultaneity in photons somehow because they're
yeah. But
massless
then
or
again,
in
the story with photons is they don't have any time at all. Time
right.
doesn't
Okay, so
mean
then
yeah.
the
Photons.
entangled particle example so like
Yeah,
I wonder what about that because that we do talk about it in time. We do say
yeah. We do.
instantly.
We do. We
So
do.
yeah,
I don't.
interesting. Okay.
I have a feeling that those two conversations are never meant to be had at the same time, and you want to put them together. Uh, and I
I'm just
think
wondering.
no, I'm sure that somebody like Brian Greene could answer that in a split second and explain
Do
what
you
the
have him
story
on speed
really
dial?
is. No, I
Oh,
don't, unfortunately. I have texted him. I know who you can text. You know what? there's a guy,
Hmm.
okay? I know a guy who actually can answer the question. This, and I recommended him often in the room. Uh, his name is Ethan Siegel. Have you heard me mention his
Yes,
name?
I have actually heard him talk as well. Yes.
Yes. So Ethan Siegel does answer emails, not necessarily personally, but he will take it as a topic.
Okay.
So I would make it three sentences. Laird says that simultaneity is impossible. And if you say that like that, it's sufficiently fuzzy. It's sufficiently fuzzy that you could easily be misinterpreting what I've said. So Laird says simultaneity is impossible. And then, and then you say that, number two, that entangled particles, when you investigate one, the other one simultaneously becomes the other. Okay, and then you say, what are we talking about here? And then
Perfect.
and then maybe we can get an answer.
Okay, that I like that. That sounds good.
Yeah. And you can quote me, even though you'll be misquoting me. Remember, I'll deny having said it because I may have been
Right.
not speaking perfectly. And I would like to know the answer to the question of whether the statement that simultaneously is impossible, in fact, carries any water whatsoever, or whether it has to be, if you will, qualified. You know what I mean?
Okay. Yeah,
Okay.
I'll bring back to you that next Tuesday with
Okay.
an answer, some sorts.
Yeah, yeah, that's good.
Thank you so much for
You're
yeah.
welcome, Ashton. Thank you very much.
Hey, Laird,
Yes.
can I say something before I jump off?
Why are you still awake? Yes, go ahead.
Well, that's exactly where I need to jump off. But
Yeah.
if anyone doesn't know that today is your birthday, I wanted to
Oh,
say happy birthday.
well, no longer, but oh yes, it's still my birthday. I
It
think
is your
every.
birthday, Laird.
Thank you. You're right. I forgot. It really is my
Happy
birthday.
birthday, Laird.
Thank you.
Yeah, happy birthday,
Happy
Liz.
birthday.
Thank you. Thank you. Anybody in the audience who
Happy
wants to
birthday.
pop up and say happy birthday and pop down is welcome to. You got 15 minutes left to do that. I am 79.
Wow.
But that's the same age as
So,
my mom,
yeah.
and her birthday was yesterday, day before yesterday.
Ah, yeah. Uh, See, I do this every week until I can't do it anymore because my brain has failed. But so far, I'm okay. Well, I'm just testing. Testing 1, 2, 3, 79, 80, 81, we'll see how that goes. All right. Thank you, Jack. Thank you for telling people that I was going to. And you got a birthday cake for me. So nice. Oh, that's so nice. Oh, thank you. Good. Thank you very much. Okay. Who would like to be next? I think Haris is next.
Good evening. Um,
Good
no,
evening.
that was a great conversation, by the way, you had with Action on light. That was really super interesting.
I wish I knew more about what I was saying. Thank you. Really.
Well, like a great teacher, you came across as really convincing.
Okay. Okay.
I thought I had it last week was like with the 9 planets that we have, they're kind of like on a except for the tilt, on a linear plane with the sun, but then the Kuiper belt's at a
Well, you got to go with 8 or 20. Okay. So Chip,
eight,
take a pick.
eight,
Okay.
eight, eight. And then and then like the Kuiper belt and other planets are are revolving around the sun at an angle.
Right.
What is about the formation of the solar system that did that? Like why isn't everything on a linear plane? Like why is the Kuiper belt revolving at an angle versus the 8 planets that
Okay.
we have?
Well, I think that the answer comes simply. I think it's one of these things that you can figure out for yourself, a homework kind of thing, an exercise left to the reader, if you will. If the solar system formed in a pancake shape, and the planets formed in the pancake, okay, then why would things further out not lie in the pancake? And the reason is simply the same reason that the solar system was formed planets in the pancake. It's because the the pancake particles eventually averaged out to be in the pancake. They weren't flying in the pancake to begin with. They were flying above the pancake and below the pancake, but they averaged out to be the pancake. But further out, there was not enough averaging.
Mm.
So that statistically, you got variations based upon there wasn't enough material to essentially create a rule. And so the rule can be above or below that plane. That's pretty much like the reason. I mean, there's more complicated versions of that same reason, but that's it.
Okay, like what? I guess follow up that to that. Like, it's like, because I'm remembering back to, like, the models and like my textbooks as a kid, and how like Pluto uh, has a long orbit that's kind of like at a 45-ish degree angle.
Not 45, but definitely askew. I'm not sure of the angle, but it could be 7 degrees. It could be 20 degrees, but certainly not 45.
Is there anything specific about, I guess, the gravitational pull of the sun that creates that kind of orbit?
No, no. The gravitational pull of the sun, is spherical. So the gravity of the sun just would produce things in orbit around it, in all different directions. But let's imagine on our Earth, we have all of these 9,000 or so satellites. Okay,
Hmm.
and they orbit not just in the plane of the equator, but north and south. They go 45 degrees north, 45 degrees south, so they can cover the north and the south of the Earth. So they're purposely put in non pancake orbit. Everything except the communication satellites at 23,000 miles, which are definitely set to be circling the Earth at the equator. So, but all the other satellites are on all different orbits. Now, the have you heard of the Kessler syndrome?
I have not.
When the Kessler syndrome, which is something we all have something to look forward to, uh, one day these satellites start crashing into one another, and more crashes produce more pieces, and more pieces produce more crashes, and eventually the entire space around the Earth is littered with pieces of satellites crashing into one another all the time. So if you have satellites crashing into one another all the time, both 45 degrees north and 45 degrees south, at some point they're going to agree on where they should stop crashing into one another, because they can't keep doing it forever, right? They're not going to do that forever. You make little itty bitty particles made of, the size of dust grains, but eventually they stop crashing into one another. And where are they all going to sit? They're all going to sit at the equator of our planet in one giant Saturn-like disk. And that's how Saturn got its rings. And that's how the solar system got its planets. Well, the planets, of course, did something else. They didn't just produce a disk. Okay, they didn't just produce a disk. They had something else going on for them called gravity. Whereas this grains of salt around the Earth wouldn't have much gravity to influence why they should clump together. So they wouldn't. So that you just get them as a ring around the Earth, but around the Sun, the self gravity of these grains would pull together. It's stronger than the gravity of the Earth of the Sun. So the gravity of the individual particles could pull together and produce planets. First planetesimals, and then ultimately planets. So and the planets are still sweeping up the planetesimals, and that's why we have meteors every night, and that's the planetesimals left over from the formation of the solar system. And they're falling down on the Earth at the rate of something like 20 tons a day. But the Earth is much bigger than that, so it doesn't mind. Uh, and it's not changing the orbit of the Earth. It's still staying in the orbit. And these planetesimals are coming mostly from the plane of our solar system, where they have been constrained by previous collisions. But all the way out there, there's not enough of these particles to essentially constrain each other. And so they, while they have formed planetesimals, so there's millions, billions, even perhaps trillions of these planetesimals out there in the Kuiper belt and the Oort cloud, uh, then but they are still so far away from one another that they never collide. So early in the solar system, they collided and made kilometer-sized planetesimals, and after that, they stopped. And so their orbits don't change over time, with a few exceptions.
Wow, thank you. Great use of imagery using satellites around
Right.
Earth
And,
to explain that. That was
and the
interesting.
few exceptions are interesting. It is thought that there are two possibilities how you can screw around with satellites with planetesimals in the outer solar system. Two ways. One is passing stars, because stars pass by our solar system every few million years. And the Earth is not millions of years, but billions of years old. So in billions of years, stars have passed by our Earth a lot. So that is one reason why the the outer dwarf planets could easily have been moved around by passing stars,
That's fascinating. Oh, okay, gotcha.
right? So the gravity of the sun is strong, but a passing sun, maybe twice as far away, has a little bit of pull to actually alter the orbit.
Oh, great.
So
Okay,
that's
that's
one
good.
way. And the other way is uh, it turns out that the galaxy isn't flat. And since the galaxy is not flat, and since we don't lie necessarily in the plane, the pancake of the galaxy, we are a little bit above or a little bit below the pancake of the galaxy. We literally are bobbing up and down between the pancake of the galaxy, and that has tidal effects on our solar system as well. So those are two things that can mess with the outer planets. But the Kuiper belt is probably not subject to that because it's really close to the sun. We're talking mostly about the Oort cloud, which is really far away from the sun.
I don't know what that is.
Well, once upon a time, there's a guy named Oort, and he invented the Oort cloud, which got his name. And what he did was he simply observed that the path of the comets that rained down upon the inner solar system had no home in the inner solar system. They come from far, far, far away, far, far, farther away than the planetesimals that we have discovered, such as Pluto, Eris, Sedna, Makemake, others. Uh, the comets come from much further away. So he said, oh, it must be that there's lots of those objects out there. Let me calculate. Oh, trillions. Oh, and how do they fall down from all the way up there? Passing stars. So that's the story. Passing stars nudge comets out of their gentle orbits and have them rain down upon the Earth. And not only is that a story, but somebody has actually said, well, wait a second. Uh, all of these mass extinctions that the Earth has suffered seem to have a periodicity. And maybe this periodicity is equal to the period with which our sun moves up and down through the galactic plane. And so that's a theory. It doesn't have a lot of weight, but it's a theory.
Wow, that's really super interesting.
Yeah, I think so.
Um, I had another question, but
Yeah,
it's
no, please.
completely
We,
escaped
we
my.
have we have four more people on the stage, and you are good with questions. So please,
Uh,
one more.
my mine is completely blinked, so we can pass on to someone else. But thank you for that answer. That was really good.
Okay, good. That was good. Great question. Thank you. You always have good questions. Thank you. Uh,
Thank you.
uh, Sarish, Surish. How do you say your name?
Hi, hello. My question is simple actually. Do you any proof that this dark matter doesn't emit microwave radiation?
Say that. Say that again.
Dark matter doesn't emit microwave radiation.
There doesn't.
Do
There
we have any
doesn't.
proof for that?
There doesn't seem to be any evidence that it emits radiation, right?
Because why I'm saying this actually, what the CMB we are observing might be from dark matter, right? It might be either reflecting or emitting
Well,
microwave radiation.
well, if you say that's so and you read that, I won't say it's not so. But I didn't know it to be a theory. Is it a theory that you've read?
No, no, I'm just suspecting.
Oh, so it's not. It's an idea that you have.
Yes, yes, yeah, my idea.
Okay, so I don't know whether that idea is a good one, uh, because I have not heard it from anyone else but you. So it may be an idea that other people have had, but I haven't seen that before. As far as I know, the temperature of the cosmic microwave background and the radiation is produced by thermal radiation. Thermal, and do you know what thermal means? It means something that's hot, and something that's hot that cooled off is what the cosmic microwave background radiation does. And it does it so well that there's a thing we talk about. Have you ever heard the word black body?
Yes,
Okay.
yeah,
So black body is a theoretical construct in which the thing is perfectly a perfect emitter and a perfect absorber. So it emits perfectly in all wavelengths, and it absorbs perfectly in all wavelengths. And as a result, the radiation that it emits is an entirely thermal radiation. And the the curve that describes the black body radiation is a very well-known theoretical curve that is extremely well understood for over 120 years, the curve of black body radiation, but we've never had a black body as good as the primordial radiation from the Big Bang. That is the best black body we've ever seen. So I wouldn't go so far as to imagining it's radiation that is emitted from dark matter. I would seriously doubt there's any evidence to support your idea. And I'll take that one to the bank. Okay. So I seem to have finished that conversation with you. And have I?
yes, yes, yeah,
Are you happy with the answer?
yeah. Thanks.
Okay. Of course, I'm not perfectly sure. I am theorizing based upon what I know. Okay. And if somebody tomorrow told me that you're right and I'm wrong, I would have no problem as long as they had a good argument for it. Okay. Okay. So let's go on to Abyss. Hi, Abyss.
Hey, Laird. Happy birthday once more.
Thank you.
It's good seeing you after such a long time. Yeah, I kind of jumped in based on the discussion you had with, I think it's Action.
Action.
Yeah, so um, I heard an alternative definition as to why there's the quantum entanglement kind of is much more, I wouldn't call it obscure, but it's kind of seems to defy logic when it comes to superluminal information transfer, when in
Yeah.
fact it's not actually an information transfer.
No,
So
there's
if
no
you,
information transfer at all.
right,
Right. Right.
right. I mean, like if you have like an entangled state, you can have like spin up or spin down
Right.
particles. But if you measure one, you can actually absolutely know the state of the other, assuming that these two are entangled.
Right.
Yeah,
Right. But he's not talking about information transfer. He didn't even talk about that. He was talking about simultaneity. In other words, until we look, they have not achieved their state. But when we look, then they achieve their state. And then when we look, it simultaneously achieves their state. And what Action was saying is really simultaneous? Because I was saying there's no such thing as simultaneous. Okay? So I wonder if I'm a little bit wrong with my statement that there's no such thing as simultaneous. You know what I mean? What I do say and hold on to is the idea that every person has has their own three-dimensional place in space and time, and everybody's three-dimensional place in space and time is theirs uniquely. That's what I say, really, and that's the one that I would repeat rather than there's no such thing as simultaneity. But so that's but there's no information transferred. So yeah.
Oh, okay, gotcha. I came into the late into the conversation, so I wasn't so sure.
Mhm.
You also mentioned something about gravitational waves and radio telescopes. I think in China, I mean, RCBO being kind of like decommissioned at this point. Or were you
Mhm.
talking about the nanograph paper, where they actually did sort of like a pulsar microarrays to essentially get sort of like the a background gravitational waves?
No, that's a different topic, but it's an interesting topic, and I know a little bit about it. Uh, over the last 15 years, so first of all, gravitational waves, the speed of gravitational waves was measured because they were able to see an object that had imploded. Two neutron stars had imploded, causing a kilonova explosion, and they were able to see that within a short period of time that they received the gravitational wave. And so it took, 10 billion years for that gravitational wave to hit us, and the light rays were seen simultaneously within a day. So within a factor of a day, error bar, they know the speed of gravitational waves is the same as light waves. That's what I was saying. Now you're bringing up an entirely other topic.
Oh, okay. I know the observation that you're talking about is collision between neutron stars. Right?
Yes,
Yeah.
right,
Okay.
right. And the topic you're talking about is they have recently, looking at the performance, the speed of which neutron stars are spinning, they have used that to measure the speed of gravitational waves, not the speed, but the currents of gravitational waves in the universe. And we can't build detectors that are big enough to detect the gravitational waves that these pulsars can detect. So looking at these pulsars, I think there was something like, I forget the number, 70 pulsars over a 15-year period. They looked and they saw that the pulsars register the gravitational waves from the Big Bang. So that's pretty cool.
Yeah, I think like the Big Bang is sort of like hypothesized. I don't know if that's actually true, but I think the most obvious candidates might have been supermassive black holes, especially
For,
like for
for,
yeah. Go
for
ahead.
what? For what? For the
No,
radio
collision
waves
of supermassive black holes.
to be
But some of
to cause the Big Bang's data?
no, no, no. I mean like
No.
the ones which were detected by the pulsar array.
Yeah, I don't know enough about it to say more than what I've said, unfortunately. I really haven't read the article, or even and hardly read the news article. So I know as much as you're going to tell me.
And I was aware of this because I interviewed one of the researchers here. We invited them here to Clubhouse uh, to talk about their research. That's why.
So tell me what they told you.
Yeah. So basically, since pulsars have sort of like a very sort of like timely um, emission rate, so basically, if the um, emissions at the sort of like the pulse actually sweeps the the solar system, that we'll be able to detect those pulsars, but their signal is actually pretty weak. So we need to have radio arrays. I mean, like radio telescopes, pretty much like the Arecibo and the one in China. I think like there's one also in West Virginia as well. So they used a bunch of these data to essentially isolate the frequencies, because like these are really weak signals.
Hmm.
So from that, they were able to deduce the mass of black holes, because like you mentioned, even though they interrogated about 70 pulsars, they have quite a distance between them. So you can essentially use each one as an antenna, and try to measure the potential delay that you're getting from one pulsar to the next. So essentially, it's about decomposing it to different frequency bands, much like what you do with Fourier transform. But I think they use much more sophisticated tools than that, and that's how like they managed to at least like positively say that these. Oops, sorry, I
Okay.
went into another room, but yeah, these could be candidates for supermassive black holes merger. Essentially, that's like the gravitational wave background in a
Right.
way. That makes
Right.
sense.
And that would have occurred earlier than the limit that we see of the cosmic microwave background, which is pinned at about 380,000 years after the Big Bang. So this
Yeah.
would be before then.
Y- Probably. At least, like one of the researchers was kind of suggesting that we're probably detecting um, primordial gravitational waves, but they're not so sure. I mean, they're not confident enough to say that that's what they're detecting. That's why I wanted to hint that. Uh,
Yes, I want
but
to
there
know
are so
what.
many authors in the paper, so
I
uh,
want to know as well. I
yeah,
have to see that more. I have to read it. Not the paper. I read the condensed version. You know, the kind of things that Dr. Becky says. She's my condensed version.
yeah,
You
I
know,
like Dr. Becky
there
too.
there are a few people out there who know what other people are talking about, and I like to read their versions. You know, Dr. Becky? Do you
Of
know her?
course,
Okay, right. Yes, she's good.
yeah, she is. Um, I had one more question, but I think like we have more people on stage, so
No, no, go ahead. Go ahead.
yeah. I mean, like last question. What do you think of the sort of like the Hubble tension at this point? I think like there is a new discovery that seemed to kind of drive the or at least like drive apart the cosmological ladder approach to that of the CMB
Yeah.
measurement. So I don't know if you have like any
Well,
opinions on that
I
one.
know that you know, if you go to the YouTube and you look at my YouTube videos, of which I have 42 hour-long videos, the last five or so were an attempt to explain to my class about the the cosmic ladder. Uh, there's another word there. The cosmic ladder that we use to figure out how far things are away from one another, and uh, and and that ladder is very important because if the ladder is wrong, then the Hubble tension, which is essentially two ways of figuring out the age of the universe, or when the age of the universe, if you will. So two different ways come up with two different answers, and one of them is based upon steps on that ladder, and if any of the steps are wrongly conceived, then perhaps there's no problem at all. So I think the most recent paper said that not only is it correctly conceived, but when you look into it more carefully, things get worse rather than better. I think that's what the paper said, although I didn't see that one either. I didn't read that. I just read the headline. Is that what the headline said?
Yeah, pretty much yes. So eventually you'll end up in two different ages of the universe, but basically, it's the measure of the cosmological constant being two different. I
Yeah.
think like the CMB actually is a bit higher than expected, with even given that the error rate compared to the cosmological ladder.
So I think this is great stuff. I like it a lot because one is based upon the local universe. In other words, let's check our local phenomenon and go outwards. And the other one is based upon let's look at the end of the universe and come inwards, if you will. So they're essentially two different domains that are being investigated by the and come up with two different numbers. And I think that's great. It means that something else is happening that we didn't know was happening. And we have to figure a way to bring those two numbers together, not like we'll ever get them to agree, but to understand why they disagree. And that's terrific. I just don't know what the answer is yet. And the fact that it's the case for them being different is stronger is even more fun. It means that people are, should definitely waste the rest of their lives trying to figure it out rather than just take a stab at it. And that if some two people if they ended up agreeing, you'd waste your life trying to explain why they disagree. But if the disagreement is real, you got yourself a career. You know, so I like it.
Yeah, I mean, I hope that it does not warrant kind of revisiting the lambda cold dark matter, the lambda CDM model itself, because that would require an entirely different.
No, I'm
Um,
hoping that there's something else going on. For example, that maybe we live in a bubble. Maybe that's true. Maybe the bubble, maybe the universe is a lot less homogeneous than we thought. Maybe really we can't judge what the universe is like from our little bubble. Maybe we get the wrong answer in our bubble. And maybe our bubble is 10 billion light years in diameter, you know?
yeah,
Because the universe is
probably.
pretty big to begin with. So maybe the answer is as simple as bigger bubbles, please. You know,
Yeah, that would definitely spin more heads.
right?
Yeah,
And they can do that. The Euclid satellite is up there, right? It's just launched, right?
yeah, I think so.
And the Euclid satellite is up there to basically say, okay, let's stop guessing what the universe looks like. Let's actually check. Because what they've been doing up to this point is they've been looking through soda straws at the universe, and and so the entire universe has been looked at maybe at the level of 1/100th of 1%, or maybe 1%, and so they really are extrapolating from 1% to 100%. Well, this Euclid satellite, I think, is going to come up to as far as 35%. Because you can't look south, you can't look in certain directions, you can't look through the Milky Way. So it's going to look where the Milky Way isn't, and and they will be able to, and they're planning to only look like 10 billion light years, no more. Because why? Because the telescope isn't strong enough to look beyond 10 billion light years. But within 10 billion light years, they'll be able to get a, the geometry of space-time. And that should be interesting.
Yeah,
Maybe they'll be able to build the ladder better. We'll find out. The Euclid satellite hasn't been up more than a few months,
right. Definitely.
right?
Yeah.
Right.
Thanks for answering my questions, Laird.
Yeah. Oh, it's always a pleasure to have you here.
Likewise.
Thanks. And Dash, welcome back.
Hey, what's going on, Dr. Laird? So I got so Before I have a question. I have questions about Newtonian gravity, but before I ask those questions, uh, your conversation with Abyss prompted me to ask the cosmic microwave background. That we is that something that we can see through our technology with our eyes, or is that
Only if
math?
if your eyes were big enough and were sensitive to microwave radiation, then yes, you could see it. But your eyes aren't big enough, and they're not sensitive to microwave radiation, so no.
No, it's like, but I'm saying like through a telescope.
Well, no, even an
That's
optical
comparable.
telescope doesn't work. It has to be a radio telescope
Ah, so what we call the cosmic microwave background is has been detected by radio
only,
technology.
only.
Okay, all right, got you.
And,
Okay.
and they've done it in different wavelengths. So they've pieced together,
Oh yeah, because
this.
radio is the longest. It can reach the longest distance, right? The radio
No, no, it's
spectrum.
not the longest distance. I mean, yes, radio does penetrate long distance, but so does infrared, for that matter. It's not because it can go long distance. It's because the space, uh, the the light, which was optically visible 13.8 billion years ago, has been stretched by the expansion of space-time, so that it's gone from the infrared to the infrared to the very far infrared to the microwave and millimeter and longer wavelengths. So it's falls in
Oh,
the domain
oh.
of radio waves, but it's
So the
not because they
light.
go further.
Oh,
It's
so the
just
light.
because it's short. The waves are longer. That's all.
So the light waves are being stretched by space.
Right. The
Gotcha.
wavelengths are being
The
stretched.
wavelengths are being. I mean, yes, the electromagnetic wavelengths are bit. Got you.
Right.
All right.
A- And and I always like to say this when it comes up, but in the old days when your TV set was getting snow on the screen when you didn't get a program, 10% of the snow on your screen was coming from the Big Bang.
Oh, what?
10% of the snow on your screen in the old analog TV days was coming from the cosmic microwave background radiation.
Oh, you got to
You
break
were
that down.
actually, your TV set was detecting that signal.
Wow. So
Cool.
our TVs, those analog TVs, were detecting the
Yeah,
cosmic microwave background.
that's right.
Wow.
And when you change the channel, you got a different wavelength from the cosmic microwave
That's
background.
crazy.
Right.
Oh
And
man.
since it's omnidirectional from all directions, it because it comes from everywhere in the sky.
Right.
So you had an antenna, but of course you couldn't tell that. It wasn't until they had a directional antenna and they pointed it up at the sky and they couldn't make the noise go away, and they tried everything, that they realized something must be happening. And even they were too stupid to realize it. So they went a couple of miles down the road to the guy who built the radio receiver. And they said to him, "Excuse me, your radio receiver has got a problem. It makes all this noise." And the guy who built the radio receiver said, "Excuse me, that's not noise. That's the Big Bang." And the people who listened got the Nobel Prize, and the people who built the radio and told them what it was didn't.
Wow.
And the people who had built the radio antenna were going to do just that experiment. They just didn't have the funding.
That's insane.
Right.
That's mind blowing, man.
Yeah. Well, if you saw the movie, if you saw the series, The Big Bang Theory,
Yes.
did you see The Big Bang Theory, the television series?
Yes, sir.
Well, in the last few
Great
episodes,
TV show.
great TV show, loved it. I love Penny. But the last few episodes, they 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 went stupid, and they had the people who observed the data did not get the Nobel Prize, and Penny and Sheldon and Maya did get the Nobel Prize for saying what it was. Essentially, they reversed the story from the actual Nobel Prize that were given to the people who discovered the Big Bang.
Wow.
I mean, can you imagine what it was like? That I mean, think of it. They, at some point, at some point, they point the telescope to the sky and they measure the temperature of the sky, and it comes in at like 3 degrees above absolute zero, and the prediction was 3 degrees above absolute zero. So they just look up and they say, "Oh my God, I can see the Big Bang." Can you imagine
Oh,
what that
zero,
felt
is
like?
it 0 Kelvin?
0 Kelvin, yeah.
Jesus.
It's just crazy.
So hold on. Okay, before because I'm getting fragmented. Um, Newtonian gravity.
Okay, yeah, go with that.
Um, so in Newtonian gravity, is gravity the force gravity that we call gravity? Is that an attractive force or a repulsive force?
Attractive.
Okay, so it that implies that if two objects, the force between two objects is the vectors are pointing towards one another
Yes.
against. Okay, so all right, so I was doing a thought experiment, right? Um, or I don't know, maybe this I don't not formally, but I was thinking. Uh, if I so if you just let's just imagine ourselves as like the god, and we're holding two planets across from one another. We're holding two planets in our left and right hand,
Okay.
and we're pulling on these planets, right?
What do you mean pulling?
Well, we're pulling away. We're pulling our arms.
So you're pulling them, you're separating them,
We're separating them. Yes.
right? Because you've got rocket engines attached to each one. Okay.
Right. Exactly. So those rocket engines, right? Is it is there anything in physics that where there's a opposing there's a repulsive force proportional to
No, there's no gravity is attractive. Period. End of story. Go home.
say that one more time.
Gravity is attractive.
Okay.
Period.
All right.
And by the way, your idea of holding it in right and left hands doesn't work because you have to be standing on something. That's why I connected rocket engines to it.
I have to be. Oh, why do I have to be standing on
If you
something?
want to hold the two planets in your right and left hand, you better be standing on something and call that thing you're standing on at rest. Because something has to be defined at rest. And and so I'm saying is if you're standing on something that's at rest, then you're pulling those things apart. But if you don't have an at rest, what you do is you have an imaginary point,
Oh,
and you
shoot.
simply take rocket engines and you point them in different directions and they separate. The point that you defined it at rest is the point that gets separated from. You don't need two hands of God.
So what you just described is that with relativity kind of uh, supplements into the way we understand gravity, like because I this Newtonian graph is so what you just explained is that a rule that was born out of Newtonian gravity or is that a rule
No,
born out of
no, I was kind of appealing to Einstein, who said essentially that that there is no place in the universe that is at rest
okay
except the place where you are. In
okay
other words, everything else is defined with respect to you. You can define yourself at being at rest. Of course, it helps if you're not sitting on the planet Earth, okay? And it
yeah
helps if you're not, because you are being thrown around by the Earth's spin and the
I
sun's
got you
rotation and all
yeah
those other things. So, notwithstanding that stuff, if you find what's called a Newtonian at rest Newtonian. In other words, you're not being accelerated, then if you say, well, I'm not being accelerated, so I'm at rest, so the rest of the universe is doing its thing, I'm at rest. Okay, you can kind of do that. Especially
Okay.
with Einstein, he says
Uh-huh.
everybody can call themselves at rest, and the rest of the universe is moving with respect to me.
Right. Okay.
Because in fact, everything in the universe is following a path, a geodesic defined by the space-time, uh, the lines of space-time. So if you throw something in a straight line, fine, it goes in a straight line. Except if you bring in Einstein into the room and he says, excuse me, it's not traveling in a straight line, it's traveling according to the geodesic defined by the masses present all around you. So when you throw a ball up in the air and it comes down, I say that Einstein would have said it traveled in a straight line along the geodesic that, in fact, it defines the curvature of space-time on the Earth. So that's why it goes up and down, because it's only following a straight line in four-dimensional space with Earth curving the space around it,
Got you. Okay.
all right?
All right.
So when
Thank
you
you.
throw that thing up in the air, it's at rest, and the universe uh, is uh, is moving with respect to it.
Got you.
Appreciate you, Dr. Laird.
Yeah. Okay. Let's go to Dave. Are you prepared, Dr. Dave? It looks like you're ruling your mighty kingdom there. I love that. I love
Well,
it.
can I? I'm sorry. Can I ask a really quick follow up to Dash's to what you just said with
Sure.
Dash?
I guess it's fair. Sure.
Thank you. So because you kind of used this ball analogy last week as well, and it made me think it's like is the appearance of it like when you throw a ball up in there, the appearance of it going up in a straight line, coming down a straight line is like because like the Earth is moving at the same time that's happening, but the
Right.
appearance so the appearance of a straight line is simply optical. It's not because
No,
it's
no,
not
no, no,
quite
no,
literal.
no. You throw a ball up, it goes in a parabola, and that's uh, and that's. But it's not a parabola. It's really part of an ellipse.
Oh wow! But the appearance to us is a straight line.
If it goes straight up and down, sure. But if you throw it, if you're having a catch, then it's traveling in a parabola, and that parabola is essentially part of a very long ellipse.
Gotcha. Okay, thank you.
Right. Okay. So next is Dave. Hello again, Dave.
Yes, sir. Happy birthday.
Thank you. No longer my
And
birthday, but thank you.
well, I just also want to say, I hope I'm as cognitive as you are when I get to that age. What's the secret?
The secret is plenty of McDonald's hamburgers, a Burger King. Don't exercise more than twice a week. Uh, Drink a lot of alcohol when you were younger. Have as much sex as you can when you're younger because it peters out. Uh, I have no phenomena. There's nothing I can recommend. It's all luck of the draw. It is completely luck. Believe me.
All right.
I,
All
I'm
right.
I'm told, I've read that, and I don't know if there's any truth to this because I read this 20 years ago, but I remember it because I liked it. It said, it said, no matter what you do, you can't change how long you're going to live by more than 2 years. You can change the quality of your life for sure, you know, but it's whether or not you're going to live any longer. I doubt it. And I think so. Unless I'm contradicted, I am of the belief that 2 years is the best you can improve your life by.
Well, there's that guy who he's spent
Kurzweil,
like
Kurzweil,
millions.
Kurzweil.
He spent millions trying to reverse his age.
Yeah, the guy's name
Uh,
is Kurzweil. Okay,
yeah.
and he is of the belief that if he takes 50 pills a day, he'll be able to live a little bit longer if they can cure whatever disease he catches. He doesn't. He's not sure he can make it because He doesn't know if he was born late enough, but what I've read recently is somebody asserting that a child born today could live forever because by the time they reach 100, it's 100 years of medicine from today. Can you imagine what medicine was like in 2023? They didn't have antibiotics in 2023. I mean, 1923. So they didn't know anything, right? They just knew that disease was caused by pathogens, but they had very few cures for it. But today we have a lot of cures for things. In 100 years from now, we'll have lots of stuff, and we might be able to reverse aging and not cause cancer at the same time. You know, so we might be able to live forever, but not you, not me.
I guess we're gonna miss that boat.
Oh
Unless
yeah.
Elon comes up with something to put us in his
Elon's a
computer.
genius, but he's crazy as well. So, I don't think his marijuana smoke is that marijuana behind you in that thing.
No, it's just a tree. It's just a tree.
It's not. It's not just. It's not a cannabis plant. It looks a bit like a cannabis plant.
I
It
guess the
looks a
secret
lot
sauce.
like a
It may
cannabis.
be. It may be. It may be. It's AI generated, so it's
Oh,
safe.
well, when I was growing cannabis, I grew cannabis when I was 20 years old, so I know what that stuff looks like.
Okay,
And
cool, cool.
that looks like it. It has not as many leaves and it had more flowers, But anyway, whatever. So my secret is don't enjoy yourself. It's later than you think.
Well, I also have some science questions as well.
Okay, good.
Yeah, you are familiar with the Carrington event, right?
Sure, sure, absolutely.
So, so my question is, during this event, and they're projecting that maybe we may be overdue for something similar
The
because this
word
happened like,
overdue isn't the right word.
yeah,
Any day it could happen. Yes,
yeah, any day.
right.
So, what exactly is being pushed out from the sun that causes this? Because it's not actually the molten uh,
No, no,
fire flame or whatever
no,
coming from the sun. It's
no.
actually something else
Okay,
altogether, right?
so
So,
so there's
what
a
exactly is happening there?
okay. So you need to know a little piece of physics, and I learned this in high school, and it's called Lenz's law, Lenz, and if you take a uh, a bar magnet, let's say, not a bar magnet, yeah, a bar magnet, not a horseshoe magnet, and you move it through a coil of wire, say through the coil of wire, and you hook the coil of wire up to a device which can measure the electricity generated, that magnetic field will generate an electric field. And that's a law of nature. And they celebrate it by using the word electromagnetism. So the story of electromagnetism in a nutshell is moving magnets create electricity, and moving electricity creates magnets. That magnetism, that's like true. Because you can make an electromagnet by putting wrapping a battery and a wire around the nail, and you get yourself an electromagnet. So it goes both ways. Magnetism, electricity, both ways. Okay, so now if you have a magnetic field coming from the sun, and if that magnetic field is sweeping past the Earth at any kind of significant speed, and if you string these wires across the United States, long electrical wires that can pick up the moving magnetic field and generate an electric current, then what you've done is you've created a transformer the size of the United States that can pick up the magnetism from the sun, convert it to electricity, and fry all our transformers. that's the, it didn't answer your question, but that's the background you need to know. Is that, did you know that, what I just said?
Yeah, I understand that part, but
Okay.
I'm just not
So,
sure how or why that happened.
okay. So first of all, so if I, so if I swept a bar magnet past the Earth, the size of the Earth, we would create that, the same Harrington effect. So you buy that, right?
Right.
Okay. So the only question is what's sweeping past the Earth? That was your original question. I didn't answer that. And so the what's sweeping past the Earth? Okay. So magnetic fields by themselves share a life with electricity, electric fields. So what you have is if you have a magnetic field, uh, you will find that the magnetic field is surrounded by a electric by electrons floating around it in sort of circles like a helix. So the electrons going around the magnetic field produce the magnetic field, and the magnetic field constrains the electrons to go around it. So what you have is you have a, a thread of magnetic field that is thrown off the sun. And what contains it is the electrons and protons that constrain it. So the sun throws off electrons and protons, right? And the electrons and protons carry with it the electric field, the magnetic field. So they impinge upon the Earth, and that sweeping magnetic field is the thing that ultimately brings down the transformers on the surface of the Earth. But it's carried by the solar wind, which is nothing more than electrons and protons. So the sun is essentially a plasma, which is protons and electrons. And one more thing, they moving around, and because they're moving around in a particular semi-organized fashion, they produce a magnetic field. And sometimes when they produce a magnetic field, it's so strong, the magnetic field prevents the electrons and protons from moving around, and that becomes something we call sunspots. And out of the sunspots, you have these looping magnetic fields, which contain an enormous amount of energy contained in the magnetic field, and electrons in a plasma in that magnetic field, jumping from one sunspot to the other. One sunspot is a north, the other sunspot is a south, and in between there's an arc like a horseshoe magnet, and sometimes those wires get twisted, and the magnetic field that's attached to the sunspots breaks away from the sunspots, and the whole coil of magnetism and plasma goes shooting off from the surface of the sun into interplanetary space and eventually hits us 3 days later. That's called a coronal mass ejection, CME.
Right. CME. So when this happens, um, it basically just interacts with the magnetic atmosphere that's surrounding Earth, right?
Right. So
And
the
it
Earth has a
it
magnetic
just
field.
supercharges that,
Right.
or yeah,
It dumps a lot of stuff into the Earth's magnetic field, and it shakes the Earth's magnetic field. So one magnetic field can shake the other magnetic field. Earth has a magnetic field. Magnetic field comes from the sun. Okay. The Earth's magnetic field is north on the north and south on the south, and the sun has a magnetic field that's north and south as well, because that's what magnetic fields do. They have norths and they have souths. Okay. And if the magnetic field coming from the sun is such that it can it does the Earth's magnetic field can sort of reject it. Nothing happens. But if it's just the right polarity, north to north and south to south, or maybe just the opposite, then all hell breaks loose, and it rattles our own magnetosphere and causes uh, the the
Borealis.
Harrington event? That's a good question, and and I have to tell you, part of my answer is incorrect. I just don't know what part of it is. Okay, so in other words, what I've said is pretty good, but I wouldn't give it 100% credulity because I haven't told that story before, and so I haven't read it in quite a while. So so for example, part of the story that I didn't get right was I told you about something happening at the surface of the sun, and then I immediately launched into a discussion of the coronal mass ejection, and that's not at the surface of the sun. Okay, so there's a couple of things I missed in that conversation, and I also missed the business about what the polarity of the magnetic field from the sun should be for it to be important. I also didn't get that right either way. But you should look it up. It's easy.
Does it gain power? I've been looking at the story of the Carrington event. Like it created such a uh, storm that it just, it was worldwide. It was global.
Sure.
Like people were seeing lights from Paris to, here.
Right. Right.
So that's wild.
Yeah. It really was. Yeah. I don't want to see that because as far as I'm concerned, if I see that, the lights are going out and they're never coming back. Because the thing
Yeah.
is, we won't have the technology to build the transformers that we need to build to replace them. So if they haven't figured out how to disconnect the transformers from this event, they won't be able to get us back online anytime soon. And I'm sorry, I don't live. We run out of food in our supermarket here after 3 days. So after a couple of weeks, everybody around me is going to start starving, and I think the whole planet's going to start. The only people left will be the preppers, and they have guns. So anyway, Dave. I want to get to two other people because the evening's late now. I want to get to Jean
One
Frederic. Do you have another
one last
question?
thing. One
Yes.
last thing.
Okay.
Which for and it's right along the subject we were just talking about
Okay.
and what you were talking about earlier. Uh, which force is actually strongest, gravity or magnetism?
Gravity's the weakest force in the universe, and magnetism is the second strongest uh, after gravity, and then comes the weak force, and then the strong force. So there's four of them, and gravity's 10 to the 40th power weaker than electromagnetism, and that's because and the only reason it's strong is because it gathers stuff together. So you have a whole planet, all right? And you're standing on the floor of your building, and the electromagnetism that keeps the molecules in the floor together is stronger than the force of gravity that's pulling you down. So electromagnetism beats gravity every time.
Okay,
Yeah,
thanks.
that
I'll remember
I'm
that
so
if I fall off a building.
yeah, right. Okay, I'm sorry. I'm cutting it short because I have two people left, and so the hour is getting late. So I want to go on to Jean Frederic.
Hey Laird, how you doing?
How are you?
Happy
Thanks for coming.
birthday. Happy
Thank you.
belated birthday.
Yes, thank you. You're outside. I can hear the wind.
Yeah, I'm trying to shield against the wind.
Okay.
You've probably been asked this a number of times, but I'm going to think about the scene in Star Wars where Luke Skywalker is looking at the double sun setting on
Uh,
Tatooine,
yeah.
right? And one is significantly brighter than the other, but they're
Correct.
only about 2 diameters apart. Has anybody sussed out what the Tatooine star system looks like
Oh yeah.
and whether or not it's possible?
It,
And
it,
if
they, yes. Go ahead.
Yeah,
And
yeah, yeah. And if Tatooine is orbiting one or the other or both, and at that point, is it possible to determine what type of stars they are
uh,
based on that single shot?
yeah, I do think I mean, I'm not 100% on this, but I think I've seen many conversations in which they discuss the idea of a Tatooine type situation. I don't know that they've found actual analogs, but I think that based upon the color and and you know, it's really hard to get a planet around a double star. It's not easy. It's in fact so not easy that pretty much they thought it couldn't be done. Uh, but the universe is cleverer than that, and we have seen planets around double stars. So the double stars have to be close together, and the planet has to be stable over 4.5 billion years, and long enough for life to have arisen on that planet. The idea of planets that, in fact, life did not arise on, and in fact could be relatively new, you know, let's say that those two stars are known because of their color, because color determines pretty much uh, what kind of star it is. And so color and diameter would pin it perfectly. And then and you have to assume an age. So you can assume either very old or very new. But if it's very old, it's really hard to get a planet to stay in a stable orbit for a long period of time. So if you imagine it's a new star system, and imagine that it's a relatively uh, uh, new planet, then you can imagine all of that stuff. So I'm sure they've found something Tatooine like out there. Uh, so it's easy.
So, in
Yeah,
a binary system, the stars would be the same age.
right, exactly.
So you can say that in this case, they're significantly different, right? One is way brighter than the other.
Right,
So it's going
and
to
that's
be either
true.
further or larger or
Right,
both.
and that's true. All binary, half the stars in the sky are binary, and they all have different, and those binaries have different sizes. They all do, every one of them, by definition, if you will, and some of them are severely different. For example, the dog star Sirius has a white dwarf companion, and you can see Sirius in the sky, but you can't see the white dwarf. So they all have, and you can and in the Big Dipper at the second star from the end of the handle, there's a double star that you can see with your naked eye as gravitationally bound. And what you can't see is each of those stars are double stars. So the star that you see in the handle of the Big Dipper is really four stars, of which you can actually see two.
So, so from this one single shot, would you be able to determine whether Tatooine is orbiting one or the other or both?
Oh, I can tell you oh, it's not scooting between one and the other,
Right.
unless one of those stars is so terribly far away that it has no gravitational influence whatsoever. So instead of those two stars being close, like it seems, that just could be an optical phenomenon. The one could be extremely far away and very big. And then it would only be orbiting one of the stars. But if you know, it rises and falls in the sky every day, that's okay. But maybe over the years, it only those two stars separate, and maybe Tatooine goes between one of those stars. That's an unlikely scenario, but still possible.
Yeah, I wouldn't imagine that Tatooine was orbiting in figure eights, but if it
Definitely not
in
figure eights. No, no way.
no, no way. But if, but I mean, if you look at the Wikipedia canon, Tatooine once was a lush planet, and now it's a desert. So the question is it basically under the influence of one versus the other as it orbits? And based on that, would you be able to fit that data with a physical model, or is it completely out of George Lucas's? I'm going to
No,
be charitable and say
if you
head.
want, no, I'm saying you could fit it. Uh, you first of all have to know the color of those stars. Remember, in a color photograph, you don't know what the filters are that put together the colors. So you have to know the colors of the filters to know exactly what the real color is of the star. And then once you knew that, then you could fit it to what's the 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 Hertzsprung Russell diagram. You know what that is, right? And,
Yes.
and so you could fit it to that because it's the color temperature uh, uh, diagram. On the one hand, on one axis is color, on the other axis is temperature. So it's well defined. I think you could tell.
Very
And then
cool.
the diameter would tell, and then you'd also know how long the day is, and if you knew how long the year was, that would be perfect. Then you'd be able to absolutely determine what the diameter would translate to in terms of actual width. But in the absence of knowing what the actual diameter is, I think you'd figure out that it's the color would determine it entirely,
So, as a professor of astrophysics,
which I'm not.
well, assuming you were a professor of astrophysics, would
Okay.
you accept this as a thesis proposal to determine the stars involved in this shot and to
Yes.
determine the
Well,
orbitals
I
and
wouldn't.
so
I'm
on?
not sure about a thesis proposal. That's too easy. I
Yeah,
would. I would take it as a paper.
as a paper.
Yeah, yeah. It's a good one because there's a limited amount of data that you're using, and and you would determine all the errors that you could possibly be found. I and then assign error bars to that. I think you could. I don't think it's a hard paper to write, especially if you uh, imagine that George Lucas used the certain kind of film to photograph the actual star, assuming you knew how the star was registered on his film.
Well, right now you could actually ask him.
Yeah. Well,
Yeah,
no, it says color by Technicolor, one of those things. You
yeah,
know?
but you could determine those parameters, I'm sure. But yeah,
Yeah.
okay, cool. So in theory, it could be a physical possibility to be Luke Skywalker looking at that scene on a life-bearing planet.
Yeah, and there's actually a beautiful movie uh, uh, that shows uh, a uh, a three stars rising and setting below the horizon on a planet that turns out to be, as you realize that the giant planet comes into view, is a moon of a giant planet. So you see three suns setting over the moon of a giant planet. It's. I would love to be able to send it to you if I could find it. It's cool.
I am going to look for that.
I'll see if I can find it, and if
But
I have it as a MP3, but I'm not sure I have it as a link.
Yeah.
Or wait, this is a good time for me to say, on my website is the links to all the stuff that I did for my astronomy course, and it's the last 42 lectures, and but the in my YouTube videos, but the links that I have on my YouTube on my website is 12 years of links. So you might be able to find it within the links. Uh, I'm not sure, but you might be able to find it. I'll take a look and send it to you if I find it.
I will dig. Thank you
Okay.
very much.
Okay. And maybe next time I'll put it up instead of my website if I have a link. Okay.
Right on.
Let me go to Christopher. And because Christopher, uh, have you been here before, Christopher? You're just listening, but I have a feeling you haven't been here on the stage before. If you're here at all, actually. Maybe not. Okay. Uh,
Well, if I can ask later, like how far apart do stars be for them to be considered a binary star system?
uh, um, hmm. uh, I don't know the answer offhand. I can make up an number. Uh, for example, Alpha Centauri and is a binary star system with Beta Centauri.
Oh, yeah,
Okay.
okay.
Uh, and there is a third star called Proxima Centauri, and it is supposedly closest to our planet, and it could be part of the Alpha Centauri system as a triple star system. But because we we can we can't easily measure the three-dimensional speed of that planet, uh, Proxima, it has been uh, tossed around as to whether or not it is in fact gravitationally captured by those two stars. I think by now they probably know the answer to that, but a while back they didn't. And Proxima Centauri is, a fractions of a light year closer to the Earth than Alpha Centauri. So certainly, I would say uh, gravitationally bound things could be fractions of a light year, if not more, depending upon the mass. You know,
Because Alpha Centauri is 4 light years away, right?
right? And you
Gotcha.
see, our star is one solar mass by definition, and stars get as big as, say, 60 or maybe even 100 solar masses. But when at 60, they only live for about 3 million years. So you wouldn't you'd see them as a flash in the pan. So even if they were gravitationally uh, bound to another star, or holding another star, they would blow up, and perhaps the remaining black hole could still constrain the other stars in the solar system. So I don't know. I'd say, a light year is a good number if you don't ask the question, how big is the star?
I'm not going there. I'm not going there. Thank
Yeah,
you.
yeah. Right. Well, has anybody in the audience want to come to the stage and wish me happy birthday? Uh, and that's just a ploy to get you on the stage, you realize. But I see people in the audience who have not at least come ever to the stage, but I've seen it in the audience, and so I, would welcome you to try your luck. But if not, we've run out of uh, uh, participants, and we will do it again next week
So,
on this channel. I have one person who has volunteered to come and maybe, I have two people who volunteered to come and wish me happy birthday. Okay, so Jeff and JJ.
Happy birthday.
Well,
Thank you
thank you.
for sharing your expertise and for your explanation of CMEs and solar weather. I would ask if you could provide a similar explanation or at least thoughts and similar level of detail on Kessler syndrome.
I think I did actually earlier. Were you here for when I was discussing Kessler syndrome?
Okay. I'll have to come back next time. I don't want to ask you to repeat
Or you can
things,
look
but
at
I'm
look at
sorry. I can go back to the replay. Yeah,
the
sorry I missed
replay.
it.
Yes, I would say the Kessler syndrome occurred at about the midpoint of the conversation. And the person who was asking the question that got me started on that, does anybody know who asked the question that got me started on talking about the Kessler
That was
syndrome?
Mia was asking about what was the creation of the Kuiper Belt and like
Right.
why.
So when Haris just first began speaking, I ended up discussing the Kessler syndrome a little bit. And please come back next week and we'll talk about it more. Okay? Good. Thank you, Jeff. And JJ, who was adopted the persona of Carl Sagan. Uh, that picture of him was taken after he was my thesis advisor. He was much younger and not gray haired at that time. Uh, I was very lucky to have him. JJ,
Hello, doctor.
how come you use his picture as your icon?
If you remember me, my last picture was M87. You
Oh,
remember me?
no, I mean, yes, I remember the MBE 7 much less than you. I mean, I'm lucky if I recognize people that are related to me. I'm serious. I mean, it's really interesting the inability. I look at my grandchildren and I say, which one is related to which of my children? You know, so I don't take offense. I don't play faces very well. Okay,
Okay.
thank you.
I would like an explanation about CFIT variables.
Okay, I know a little. Uh, uh, what do you want to know?
How do they work? How do we calculate the distance of the galaxies, and how do we measure the expansion of the universe?
I'll tell you a little, okay? Uh,
Okay.
and then that'll be my last question, okay? Because it is over the time limit, more or less. But so the first question is why are they variable, right? Uh, and and I have studied that, but I don't remember the answer. But it has something to do with the fact that they exhaust a certain amount of their fuel, and then for a while, they are not burning anything, or at least at the same rate, and so they cool off, and they're not as bright, or their envelope becomes bigger, as one of the two, or maybe both. So they get bigger, and when they get bigger, they get brighter. So and the size of and their period is related to their maximum luminosity. I don't remember whether or not it's the bigger ones are the the ones with the longest period are more luminous or less luminous. I don't remember that relationship. But there's the relationship that luminosity and periodicity are linear and can be described by a graph. Now, if you know the absolute distance to these Cepheid variables, then you know their absolute luminosity, and because you know their distance. And then you see, well, that level of light bulb is in fact, when it varies at this rate, I can say, when something varies at that rate, it's that luminous. And when I see something that I also know the distance to, and it varies at a different rate, and it is differently luminous, then I can say, oh, I have now two data points. If you get a set of data points like 30 data points, where you know the distance of 30 Cepheid variables, then you can literally say, aha, I know an absolutely perfect relationship between distance and luminosity and brightness and period. I'm sorry. And then with that information, you can, if you see something that you don't know the distance, but you can see the period, you can say, aha, I know I see the relative brightness, but I know what its absolute brightness is, and I can figure out what the distance is as a result. Now, did you know what I just said, or is our question more complicated than that?
Uh, I want to make a distinction between Cepheid variables and Type 1a supernova.
Well, there's no relationship, okay? What is the relationship is that you what you'd use. They're both stepping stones on the cosmic ladder. That's the relationship. That's what you mean? Is that what you mean?
Mm, actually, I know we use type 1a supernovae and CFIT variables to measure the distance. I want to make a
Right.
distinction between them, but I
Okay.
don't know how.
Well, first of all, one is one and one is the other. One is an apple, one is an orange. Okay, so they're not related. Okay, except for the fact that they're used in the same sentence. And the so the Cepheid variables are useful for measuring the distance to nearby galaxies. So if you can see a Cepheid variable in a galaxy whose distance is unknown to you, the Cepheid variable will tell you how far the galaxy is. So you're able to see how far away the nearby galaxies are by looking at the individual Cepheid variables that you can distinguish. So you get distance relations for all the nearby galaxies. And because a galaxy, on the average, has a supernova every 100 years, and if you have uh, a, uh, a, uh, uh, a supernova that goes on in a galaxy that is known distance, then you now know the absolute brightness of that supernova, not the relative brightness, but the absolute brightness. And then you can say, well, if all type 1a supernovas are the same brightness, then if I can distinguish type 1a supernovas as being, oh, that's a type 1, that's a type 1a, that's a type 1a, that's a. So every time I see a type 1a supernova, I can then tell you what the absolute distance is to that galaxy. But I needed the Cepheid variables to get me there. I need a few of them nearby so I can be able to then use the type 1a supernovas for the rest of the distance measurements. And that takes us out to the end of the universe.
Yeah, thank you, doctor.
Right. But the question is, did they get that right perfectly? In other words, did they measure those things well enough to be absolutely certain? And the questions are constantly coming up because people want the answers to be wrong. Because if you can say that somebody got the wrong answer, then you have a whole new theory you got going. You know, because the universe is measured this way. And if the universe is badly measured, either from, like you say, well, that's a Cepheid variable. How do you know? How do you know that's a Cepheid variable? Maybe it's not. Maybe it's something that looks like a Cepheid variable. And maybe what its periodicity is in fact false. And in fact, it's true. They found that there's two kinds of Cepheid variables, not just one type. So you got to get it right. And type 1a supernovas turns out to be that there's many types of type 1a supernovas. And there's not just one simple type. So Cepheid variables are discussable, type 1a supernovas are discussable. So that's where the magic comes in, getting that right.
Uh, I thought type 1a supernovas are all the same.
Yes, but look it up. It's not. It's arguably different. Arguably different. So the question is, can we distinguish between all the different types of type 1a supernovas? See, so that makes it.
Doctor, can you give me a reference for
Oh
different
no,
types of type 1a supernovas?
no. Ask
Because I thought,
ChatGPT. Ask ChatGPT. You know,
okay.
ask ChatGPT because it'll point you maybe in the right direction. It doesn't give references, which is unfortunate. But ask ChatGPT if there's different types of type 1a supernova and how you distinguish between them. Let me just say to the rest of the audience, I'll tell you what it's type Y. I'll tell you why we think it's the same, and then you can draw your own conclusions why it's different. Uh, so that uh, so once upon a time, there's a guy named Eddington and he decided on the basis of his mathematics that that if you uh, keep adding uh,
Doctor
ma-
was Chandrasekhar, right?
yes, it was Chandrasekhar, not Eddington.
Yeah.
Thank you. And if you keep adding mass to a star, at some point it'll simply blow up. Okay. So how do you gently add mass to a star? And the way you do it is it's a binary star. One is small, and one is large. One is the one that is one of them is a red giant, and so it's got a giant atmosphere, and the giant atmosphere is leaking onto the other star, and by because the other star is pulling, you know, streams of matter from the big red giant onto its surface, and slowly but surely, at some point, the little star, and I don't mean really little, but I mean it's by its nature littler. The littler star gets too much mass, and it simply blows up. But it blows up at exactly the same size each time. So when the star reaches a certain size, it blows up and it has a certain, exactly the same luminosity every time. But that's the story of how you make it. But the story isn't, that's not the way actual stars work. It's much more complicated than that because they have their own story to tell. So each each star isn't quite as simple as the little story I just told. And that's why there's a range of them. But they take that into account. That is all taken into account by the people who do this stuff. It's the third order stuff that is still laying in wait for people to screw around with. But you should find out about the second order stuff, instead of the first order. First order is type 1A, that's it. Second order is what are the various uh, ways you can make a type 1A. And are they all the same luminosity? And how do you determine the difference? So I think I'll look that up myself. I want to know.
So, doctor, you mean type 1A supernovas are the same, but there are different ways to make it, right?
Right, and they're not exactly the same, so they're not exactly the same brightness. So there's many different ways, and maybe you got one wrong. So I'm not, I don't know enough about this, but I do know that in recent years they have been very much more careful about what they're saying about these things. In the beginning, it was simple. No, it's no longer simple. So you should find out what the nuances are. I think I'll do that too. All right. So I think this is the end of time, or at least the end of my time, and with you. So do check out my YouTube videos. Watch them, turn them on, and go to sleep with them, so I get more viewing time. And don't forget to like them and uh, do that. I have 9 YouTube TikTok videos that are instead of being an hour long, they're 15 seconds long, and they were just done as an experiment. But I kind of like them, even though they're just amateur stuff. So is my YouTube videos. But check them out because you can see me, talking in real life. And check out my website for the links over the years that I was lecturing. And I'll see you next week. And next week it won't be small steps and giant leaps. It will be astronomy and astrophysics. I alternate between each week. And and Jean-Frédéric, I'll see if I can find that Tatooine uh, pic. It's not Tatooine, but seeing 3 suns rise or set is really cool. And then the big planet looms into view. It's really cool. Okay. Oh, and Barry, you haven't spoken, so I'm sorry. Did you not speak? Uh,
Oh yeah, sorry. Morning.
yeah,
Well, I don't know what time it is. Morning over here.
yeah. Where are
Yeah.
you? Where's
I actually,
where's
yes, sir.
here? Where's here?
Nigeria.
Oh, okay. Uh,
Yeah.
wow.
Yeah. Yeah. So I was actually going to comment about when you were talking about synchronicity. I don't know if the guy you're talking to is still here,
No, he's
though.
not. I don't think. But also,
He's not.
I made a lot of qualifications, so I hope I don't uh, get into any further trouble. Go on.
No, no, no. I don't think you. I don't think you did. All right. So what I was going to say was, um, thanks to what is it, time dilation or relativity, the only way you could ever truly synchronize two clocks would be if they were occupying the same space at the same time.
That's what I was saying exactly.
Yeah, that's. I'll just try to clarify that to him. Like that's really, and it's impossible for even an atom or for anything to occupy the same space at the same time with another atom. So it's always going to be unsynchronized. Yeah,
Right. On the
that's
basis of that
yeah,
observation is what I said. Everything else that I said. Yes.
yeah. That's what I was going to point out. Yes, yeah.
Right. And do you agree with that statement?
Oh yeah, it makes perfect sense. I mean, I never thought about it until that moment, but once I
Uh-huh.
did, it just yeah, the penny drops and it made perfect sense.
Uh-huh.
It makes
Good.
perfect sense.
Right. Ah, so Nigeria. Yeah, I forgot. Right.
Yeah.
Uh, yes. Well, welcome back, and we have to go.
All right.
I'm glad that we did this, and do come back next week. I won't know any more next week than I did this week, but the questions will be different. So I seem to have a lot of knowledge. It seems to come and go, mostly go as I get older. But 1 year more, one less year to go. Uh, so thank you all for wishing me happy birthday, and I'll see you next week,
Thank you,
11
Laird.
o'clock Eastern Time.
Thank you
Uh,
very much.
and
Thank you, Dr.
the name
Laird.
is
Happy
Laird
birthday to
Whitehill.
you.
Thank you, Laird Whitehill on YouTube videos. And I'll see you next week. Take care. Bye bye.
Bye.